Hello friends, welcome to our channel. Let's have a look at a newly appeared problem. Problem 3685. Subsequence sum with after camping elements. So this is actually a slightly harder problem because here we are considering subsequence, not subarray. So actually for this problem, a natural extension is that if the subsequence is changed to be subarray. So how do you solve this problem? Actually, if you change this to be subarray, the problem becomes a little bit easier, right? So here, let me state the main requirement. The main requirement is that so an array capped by a value x is obtaining by replacing every element with the smaller of this number with x, right? So once you are above x, you will count as x. So here the sense is that for each integer x from 1 to n, where n is the length of this given array nums, or a, I change it here to be a just for convenience of typing. So we want to determine if it's possible to choose a subsequence from the array capital X such that the sum of the chosen element is exactly key, right? So first you need to notice that here we are considering subsequence, and therefore the order of the element which can sum to the target key is not important. Therefore we can use sort, right? So here you can look at the two examples. If you look at the constraints, so the length is bounded above by 4000, and the key can be also as large as 4000. So if you multiply them together, it's 16 times 10 to the power 6, a decent large number. So here, what we are going to do is to use dynamic programming. But in order to save the sums achievable, we are going to use bitmask. So basically, a sum S is achievable if the bitmask or DP number, so we just use a DP number, so add this one, so it's non-zero. So if this guy is non-zero, actually it's nothing but 2 to the power g, right? In other words, this second half. In other words, we want the j's position is set. In other words, it's 1. So the main procedure will be the following. We first sort the array A, and then we are going to use this dp. So this is just a integer number to track all the achievable sum for g less than or equal to k using element processed so far. So here there's something you need to understand is that as the cap x increases from 1 to n, so we iterate through all the element less than or equal to the cap x, right? And then we update the mask. This is the update, right? So originally there are some positions can be achieved. Then, so if you can achieve at g, so you add all the bit positions to the shift to the left by this amount, meaning that so this new bit position is actually corresponding to the sum. And then we do the union because original sum is also achievable, right? So this actually can be equally done using a set. But for this problem, if you use a set, it will be time limited, right? So this is the one way to find the sum achievable by element capped to their original value so far, right? So if given a cap value, so for all the remaining elements, so there will be n minus I of them will be capped at x. So we just need to check if we choose 1x and 2x, 3x, if we can realize the target key, right? So this is actually the overall procedure. So now let me look at the code, and then let's first do the coding, and then later we do some print to reveal the full details. First, we can sort this one from small to large in order to suit the increasing from 1 to n of this x. Also, let me define this n, right? So we want to have a array. So originally we set all the position to be false, right? If a cap corresponding to the achievable key, so we are going to set it to be true. So this is the final state of this result is what we want to return. So now let's use this dp as 1. So 1 means 0 is achievable originally, right? Just because the binary representation of this dp is nothing but say 0, 0, 0, 0, 1, right? So the 0th position is achievable, means the sum 0 is achievable. And then we can have a mask. So the mask actually is just to restrict the value of the dp, because if the position is larger than the key, right? So we don't care about that because the sum is the most key. So for this we need actually 1, 1, 1. So in other words, key ones, right? So how do we do this? So we can do this to 1 shift to the right, key plus 1 position, right? And then what you do, you minus 1. So then this will give you all ones. For example, let's give you an example here. If k is, let's use this first example, is 5. So then I shift 1 to the left 6 unit. So it's going to be 1, so 0, 0, 0, 0, 6, 0, right? Then I use this 1 shift to the 6, then minus 1. What I get is nothing but this position is gone, right? So we have 6 ones, right? So then if you count bit position, so this is the bit position 0, this is 1, this is 2, 3, 4, 5, right? So if you have a dp value like this, it means the sum 0, 1, 2, 3, 4, 5 are all achievable, right? So but we just use this mask to restrict the range of this dp. So you can choose not to use it, but it will be slower. So next, originally we look at element at index 0, right? So now let's iterate. So for x in range, so 1 to n. So here we write n plus 1. So now let's see if while I is less than n is inbound and ai is less than or equal to x. So what do we do? So we do dp update, right? So dp union is this dp shift to the right, this unit. So here actually this will do the job, but you can choose to use this mask to restrict this value. Here let me give you a example. So for here example 1, so we have after sort we have 2, 3, 4, 4. So originally the dp is 1, right? So now if you have you processed 2, for example, just for example if you process 2, so but here if x equals 1 you do not process 2, but I just want to use this one to get an idea. So originally you can only achieve 0, but if you process 2, so dp will be something like this. dp because dp union this original dp shift to the left 2 units. So it's going to be let's use 0, 0, 1, and with this dp shift to left 2 units. It means that you have say 1, 0, 1. It means now you can achieve 0, you can achieve 2. But now if you shift dp, if you also process 3, right, then the dp will be dp union dp like this. So it means this, right? So originally you have let's use this 0, 1, 1, 1, 1. So this is the original value 1, 1. But then you also shift let me add another 0. So you shift this dp 3 to the left. So it's going to be 0, 1, 1. So 0, 0, right? So this means 0 and 2 can be achieved. So then because 0 and 2 can be achieved, then if you add 3, then it means 3 and 5 can be achieved. So here is bit position 3, this bit position 5. So union, you get 1 0 1 101. It means the sum 0 is achievable, 2 is achievable, 3 is achievable, and 5 is achievable. Because here we are processing 2 and 3. So if you do not choose, you get 0. If you choose 2, you get 2. If you choose 3, you get 3. If you choose both, you get 5, right? That's the logic. So once we have this, so we can increment I by 1, right? So now, so after this, so there are n minus I items is strictly greater than x. So we are going to cap them to x. And so we can think of we have n minus I x, right? So now so we can choose 0, we can choose 1x, we can choose 2x, but we can only choose x. So here let's see how should we construct the using this elements. So we can have k modulo x. So why we have this? Because the original one can only give you multiples of x. So the remainder of this k over x must from the origin the previous status of dp, right? So then also you can have so k minus n minus I times x. So this value can be negative, right? So you choose the maximum one, and then you check for j in range, so v and k plus 1. Then you use step x, right? So then we check if this sum, if dp add 1 shift to the j. So if this g sum g can be achieved, so then we are going to set a result x minus 1 to be true, because here 1 is from 1 to n plus 1, from n is corresponding to 1 indexing, so we minus 1 corresponding to the 0 indexing in the result. So then once we have already make it reachable, so we just don't need to do further check. So then we can return this result. So this is the full code. Let me first run to make sure it works. So here it's not. Let me check what's the problem. So here 1 OG, so break. So here so x is 1 to n plus 1, while I is less than n, and this is then dp is dp, this is right, and then I plus 1, so v k modulo x, and then k minus. So for j in range v k plus 1 dp 1 j, yeah. So let me check again, sort, and then dp is 1, mask is this. And then I equals 0. So yeah, I think here I put all this thing out of the for loop, so I should put it here. So now let's check that. Yeah, it passes the 2 test cases. Now let's look at the generic case. It passes all the cases. So first comment. So here this line. So for this line, we use this mask to restrict, because the mask is like the 5 ones, 6 ones in using example 1, right? At most, so this dp is having 6 ones or smaller. But if you do not use this one, it also works. But this number can be large because you keep shifting to the left. But for our purpose, we only care about the in total k plus 1 bit position. In other words, the highest bit position is k, right? So if you do this check, it also works. But slower. Let me see. This is the first comment. The second comment. So here I'm using dp to store the achievable sums, but you can use set. but it will time limited. Let me do some print so that you know the procedure. So here, let me do this print. So here print. So here let's see x, and also let's print out this I status and also dp. So this dp is let's use binary, right? And then let's also the mask. Mask is identical, so we just make like this, and also we print put one here, and then put an empty line. So let's see. So if you look at the first example, so if after a sort, so you are going to have let's see. Also, let me print out this one. Print out this a, right, after sort. So after sort, you will get this 2, 3, 4, 4. So when I equals 0, because your x is 1, you cannot pass anything. So you can only achieve 0, right? So then when x equals 1, so when x equals 2, you can pass this one. So originally you can have some 0 achievable, but now you can have 0 and 2. So this is the 0 and 2. And then when you add x equals 3, you can pass this 2. So the achievable sums will be 0, 2, 3, and 5. So 0, 2, 3, and 5. When you pass x and 4, so you can pass all the things. But the ones we are interested in, we can achieve is still 0, 2, 3, 4, 5. But larger ones, like you can achieve like use all of them. You get 5 plus 8, 13. Plus 13, we have used this mask to cut it, right? So when x equals 3, so let me give you a walkthrough for this one. So when x equals 3, I equals 2. So when I equals 2, so we have then here let's see. So a quick walkthrough. So when x equals 3, so when x equals 3, the dp is this, and I is 2, right? So here, therefore, you have this v. What we want to check is v in this range, So k modulo is 5, modulo 3 is 2, right? Then we have 5 minus 2 times 3, so this is negative 1. So I get so let's see, v is this larger one, so max this will be 2. So we want g in range, so v, that is 3, 2, and then 5 plus 1 is 6, so with the gap 3. So in other words, so we have iterate 2, 5. So we want to check if the sum 2 or 5 is achievable. So if 2 is achievable, because we just need to use advanced 3 here, right? If 5 is achievable, so 2 corresponds to using 1, 3, right? And 5 corresponds to using 0, 3, right? So why don't we have 2 3s? Because 2 3s will be larger than the target 5. That's why we have this starting from this modulo, the remainder. The reason that the remaining items, that is the 2 3s, cannot contribute to the remainder part. So now we check 2. So because here this 2 is achievable, right? So then actually you can check 1 shift to the right by 2, and then add with this dp, this number. So it's nothing but this number, right? Therefore, so we set dp this result at index 2 to be true, right? So that's a quick walkthrough. So you can similarly do the 4, because at 4, so this is the index, right? So you can have 0 threads, but you already can have 5 directly. So with that said, I guess that's basically about it for the current problem. So this is the one way to write this. So to sum up, we used a sort and we used a bit operations, and also we used this one, because if you kept a list, then the only choice is that you choose 0 x, you choose 2x, 1x, you choose 2x, or you choose the number of x available, right? So with that said, that's it for the current video. Thank you for watching.